Hello everyone, welcome back. In this video we're going to talk about phase diagrams and how we map the state of the phase or the state of matter at different temperatures and pressures. So as we can change phases of material both by changing the pressure and by changing the temperature. Changing the temperature is probably what we are most familiar with. We put water on the stove and we turn on the heat and it starts to boil and it turns into gas. Or we put water in our ice cube trays and we stick it in the freezer and it gets cold enough and it turns into solid. But it turns out that everything that we can do with temperature, we can also do with pressure. And so phase diagrams are working to map the phase of the substance that exists at different temperatures and pressures. Now, within the phase diagram, there are these lines that exist. These are known as phase boundaries. When we happen to be at a temperature and a pressure such that we exist on a phase boundary, it means that multiple phases exist. So here where I drew the dot on this phase boundary, solid carbon dioxide and gaseous carbon dioxide would both coexist. There's another important point along the phase diagram, and that is what is known as the triple point. And this is the point where all three phases exist simultaneously. And so this is the only point on the curve, on the phase diagram, in which the solid, the liquid, and the gas can all exist. Now, in this phase diagram, there is what is known as a critical point. When we pass the critical point, in both temperature and pressure, we enter into a region known as the supercritical fluid. And the supercritical fluid is another state of matter. Just like solids are very different than liquids, are very different than gases, supercritical fluids are different than solid, liquids, and gases. In supercritical fluids, these really behave a lot like a liquid. They kind of have the same viscosity sorts of ideas. But in a supercritical fluid, properties such as intermolecular forces are completely different. And so we often use supercritical fluids for extractions because things that aren't normally soluble in liquid sometimes often become soluble in supercritical fluids. And so supercritical CO2 is actually what is used to decaffeinate coffee because the caffeine is very soluble in supercritical CO2. So we can extract out the caffeine and then raise the temperature or lower the pressure, and the supercritical fluid turns into a gas and just leaves. And so we don't have any solvent or waste to have to deal with. Now, these properties and how supercritical fluids work and exactly what they are is an area of active research. And so it's okay if you're like, I don't really understand how this is different than a liquid or a gas. Just know that it's different in the same way that a solid and a liquid are not the same. So, reading the phase diagram, what we do is we really look at a temperature and a pressure and we see what region of the phase diagram we happen to fall in. So at room temperature, 300 Kelvin, and atmospheric pressure, 1 bar, notice that this is on a log scale, and so the log of 1 is 0. So whenever I put these together, the point corresponding to those is here, right in the middle of gas. And so, as we would expect, at room temperature and pressure, carbon dioxide is a gas. That's what we're exhaling. I'm glad it's not a liquid. Now, this phase diagram can help us figure out what happens if we change the temperature and the pressure. So if we start at our room temperature gas and we lower the temperature without changing the pressure, and let's say we lower the temperature to say 100 Kelvin, at that point we transition from a gas to a solid, and so we have a phase transition known as deposition that has occurred. Now, the same thing can happen with changing the pressure. So if we start at, I didn't start at room temperature. I started slightly below room temperature, like 250 Kelvin. And we raised the pressure up to, I went up to like 31, 32 bar. The carbon dioxide goes starting from the gas and it enters into the liquid. And so we have condensation that occurs with changing those properties. Now, if we ask what phase of CO2 exists at 200 Kelvin and 1.5 bar, that lands us on this phase boundary. And so it is going to be a solid and a gas. Okay, so really, phase diagrams are here to help us figure out when we have a set of conditions, a temperature and a pressure, what do we expect? And it also helps us to design our experiments, that if we want to make sure that we are working with gases, then we need to stay in the part of the phase diagram that gives us a gas. We need to make sure not to raise the pressure so high that our CO2 turns into a liquid, or not lower our temperature so far that our CO2 turns into a solid. Okay, so phase diagrams are really there to try to help you figure out what changes and what states exist at different temperatures and pressures.